Hey everyone, just coming in for lesson 9. We're just gonna wrap up Gaussian elimination today. I'm just gonna close my WhatsApp there in the background. I'm gonna keep it a bit of a short video today. I actually meant to record and put this up a little bit earlier, but I completely forgot. So here we are. We're just gonna focus on wrapping up the code. There's really not much to be said about Gaussian elimination that I haven't already said, and we already finished the forward elimination in the last video. We're just doing back substitution and wrapping up the whole thing right now real quick. So for that, I'm just going to write a function called backsub. We're just going to continue on from the same notebook we were in before. We take a comma b. I'm just going to call it a underscore u to denote to myself as the upper triangular the upper triangular matrix that we got from the forward elimination. This has got to return a vector x, which is none. It's going to be the same size as AU. I'm not going to do any checks or anything like that just to make this quick, though I do recommend you do so when you're doing this on your own to give yourself a bit of a challenge. So this is none for underscore k, no, for range, for underscore in range len, I'll just do b. It's the same difference anyways, okay? So x -1 is equal to it's pretty simply x -1, so the last element is essentially just what would it be? It should just be b -1 divided by a underscore u, last row, last column, right? That'll just essentially be the last, and then for the rest we have to do a loop, which would work out in some way, shape, or form. Normally I wouldn't do this, and I would not recommend you do this, but it's just super late for me and I forgot to get to this earlier, so I'm just gonna go ahead and look up that pseudocode that I was using earlier. I think it's in this one. Yep. Okay, so this is basically it. So for idx in range len b -1, that's our start. Our stop is -1, and we're taking reverse steps. So the very last row, back substitution, we already solved here. What do we want to do from here on? Right? See, a n end over a n n. So we do for I in n-1 down to 1, right? So from the second last position down to the last position. Actually, we'll do len -2. Oops. Just changed my brightness for no reason. Right, because the very last row we already took care of, and we subtract another one because len b would be like, say, 5. So for example, if it's a 5 by 5 matrix, len will be 5, but the actual index range starts one below, right? And we want to go one below that even because we already do the last one, right? Here we're essentially doing the sum of j equals I plus 1 through till n aij times xj. Is that correct? Oof. That doesn't make sense. This makes more sense. Oh no, this is for pivoting. Well, this is the pseudocode. Let's just focus on this example and that should help me. For I equals n minus 1 down to n. And you know what? If you do need to refer to things, I would suggest looking at the math and trying to understand things through that, you know? And just in general, you know, try to think about things in an abstract way. That really always helps. Anyways, so C is B. I'm just gonna, I call it B, right? Let's just follow it with the symbols down to the T. Minus sum of uij xj for j equals I plus 1 through till n. So let's just call this, oops, make ourselves easier and call I, right? So for j in range len range I plus 1 through till len b, right? Let's just say all the way through to the end, right? We want to do the sum of uij, so a underscore u I j. Now ideally I'd be asking you times xj, right? So if you think about this, so looking at this at the first iteration, let's say we have a 4x4 matrix, right? This will start at index 2, right? Because 4x4 would lead len 4, right? And then we'd get the index of 2, right? Because 4 minus 2, len b minus 2 is 2. Index 2 meaning the third row in a 4x4 matrix, right? And we're taking bi, so that particular element, bi, so in the second last row, minus sum of a u, so from the upper triangular form, ij, so that row, so second last row, second last element, right, in the first iteration at least, j starts at I plus 1, right? Wait, that doesn't make much sense, does it? So in, for example, this matrix we're looking at over here, let's look at a worked example. So in the second iteration, let's just Let's go through a Gaussian elimination example and try and think this out. Okay, so we already, in this example, we take 9 divided by 3, so that's our first value of x, or the last value of x, right? Then we come up here, right? We're looking at this item, bi. Bi in the first iteration would be this -3 minus the sum of auij, so this one, right? Ij would be this, because j would be I plus 1, right? And I is 2, so j would be 3, right? And we multiply that with xj, right? Because we know xj in this particular situation would have been 9 divided by 3, 3, so -3 times 3, right? So this minus this times 3, 9 divided by 3, 3, right? And then divide all of that by this, right? So if you could imagine these as a system of linear equations, that makes perfect sense, right? Because that's the point of getting it to the upper triangular form. Imagining if each of these columns were x, y, and z, the coefficients, right? You'd just get 3z equals 9, so you'd get z equals 9 divided by 3, 3, and then, yeah, okay, so the algorithm checks out. This makes sense. And we do this whole thing, right, divided by a underscore u I, right? And that's what xi equals. I believe that's all there is to back substitution, right? And just putting it all together, we'll call something Gaussian elim, a comma b, right? We put it through forward elimination, a comma b. Those are changed in place, so we don't need to assign anything. If you don't remember, you can check that out from the previous one or from this code here. There is no return. I am just changing the matrix in place. And then I just return back sub a comma b, right? Let me execute that cell. I'm just gonna super quickly pull out my test cases, which is, I believe it's these. Command A, C, yep it is. Command V. Okay, I'm just gonna rename this solve Gaussian just to have the naming consistent, so I don't have to rename the names here in each of these tests. And all the asserts passed, and we're done. Super short video. Sorry about that, but I'll try to make it up to you guys soon. We'll have like a nice meaty video coming up. I'm doing Gram-Schmidt ortho normalization next, which I'm not having nearly as much trouble with in terms of putting it into an algorithm the way I was with Gaussian elimination, because with that I was actually having trouble picturing and doing the algorithm itself. And that was my mistake. I think I should have focused on doing the pseudocode and like doing a couple of iterations by hand to seeing how things work out, and that would have helped a lot. But I did spend a lot of time just understanding what orthonormalization is. I could figure it out from the word. It's, or normalization, where the vectors are also made to be orthogonal in some way. But understanding the uses and the process in a geometric sense, in an abstract sense, that took me a while. So I'll try and talk about that in the next video. It might not even be like a proper lesson video like one of these, and just like one of my behind the scenes, like I'm just thinking about stuff and organizing the thoughts in my head kind of video. But anyways, thank you all for watching. Have a great one. Good night.